Today we're going to learn Chapter 6, Capacitance and Inductance. This is part 1. The course objectives include analyzing circuits with capacitance and inductance. And in this module, we're going to learn how to use circuit models for inductors and capacitors to calculate voltage, current, and power. We're also going to learn how to calculate energy stored in capacitors and inductors, how to describe the concepts of a continuity of a current for an inductor or continuity of a voltage for a capacitor. So capacitors and inductors, they are also passive elements. They are also energy storage device. So capacitors, they store energy in an electric field. It's an electrostatic energy. And the inductors, on the other side, it stores energy in the magnetic field. It's an electromagnetic energy. So let's look at it more in details about this energy storage device. Over here, we have a picture about a capacitor. A capacitor is formed by having two plates placed face to face. And in the middle, normally these are filled with dielectrical material. For this type of capacitors, if you open it, you will see a big fume, and this fume will roll together to form a cylinder shape like this. Normally there is also some fluid inside, and that fluid is a type of dielectrical material. And a circuit representation, you can draw a capacitor like this with two plates and two terminals. You can also draw it like this if the capacitor have a specified reference polarity. So normally for capacitors like this, you will see them with a label of reference polarity. You cannot install them in a reverse direction if they have a specified reference polarity. Calculations related to capacitors. The basic capacitance law, it says that the charge on the capacitor is a function of a voltage applied on the capacitor. So this function can be linear or can be nonlinear. And for linear capacitors, it obeys Coulomb's law, which says the charge on the capacitor is equal to a constant C times the voltage applied on it. So if you apply a voltage Vc on the two sides of this capacitor, when it reaches steady state, and this will be the amount of charge it can hold. Throughout the whole process, the voltage is always linearly related to the charge. Capacitance has a unit of a farad, and it's a derived unit. And from the definition, we know that this unit for this capacitance C is equal to Coulomb per volt. From the construction of a capacitor, we find that the capacitance is related to the area of the surface and also the distance between the two surfaces, and also eta. Eta is a dielectric constant of a material in this gap. Here I have a simple example. To determine the voltage across a 2 μF capacitor holding 10 millicoulomb of charge, so we can calculate by using this relationship. The charge is always equal to a constant C times the voltage. So the voltage Vc is equal to the charge divided by the capacitance of this capacitor. So that is how we calculate the voltage across a capacitor. We can see that although this capacitor doesn't hold a lot of charge, but it can have a voltage of 5,000 volts. So capacitors can be dangerous. We learned the basic Coulomb's law, which describes the relationship between the voltage and also the charge the capacitor holds. And we also know that the charge rate is equal to current. So if we take a derivative of this equation versus time t, we will find the left-hand side is dq over dt, which is the current I. The right-hand side, because c is a constant, we keep c, and it will become dv over dt. So we can see this equation is derived from the capacitance law. This equation is very important, and all the calculations related to capacitors, you will need this equation. The current going through this capacitor is equal to the capacitance C times the rate change of the voltage. By giving these two basic relationships, we can also calculate the voltage on a capacitor. If we want to calculate the voltage on this capacitor, we need to divide the C to the left-hand side, then we do the integration. So that is how we calculate the voltage. And from this equation, we know that the voltage is following this integration form. it implies the voltage is continuous. The continuity is described as V at T minus is equal to V at T plus. So the voltage on the capacitor is always continuous. Current is equal to C dV over dt. In steady state, when Vt become a constant and dV over dt, that becomes 0. So it means the current I is equal to 0. So in steady state, a capacitor acts like an open circuit. So now we put all the equations together into one page to summarize everything you need to know about a capacitor over here. So if you want to calculate the instantaneous power, P, and we know that it can be calculated by using the voltage on it times the current going through it. Since we know the current is equal to C dV dt, and we can calculate the power, we submit this equation into the previous one, it becomes CVT times dV dt. Because we have Vt over here, this is dVt, we can write it as C dd half V squared. And if we integrate the power over time, then we can calculate the energy stored in the device. And if we integrate this term over the time period from T1 to T2, and we can see that the energy is equal to half C V squared T2 minus half C V squared T1. And in the problem, if you know that at time T1, the energy is equal to 0, in that case, the energy at any time t is equal to half C Vt squared. And from the right hand side, we know the voltage can be calculated by using this integration form. Replace the voltage term by this integration term, we get the power can be calculated by using 1 over C times d over dt half q squared t. And if we do the integration, do the same thing, we do the integration, we can find the energy stored in this device that is equal to 1 over C times q squared minus 1 over C times q squared at time t1. And if we know the energy at a time t1 is equal to 0, the energy at any time t will become 1 over C times q squared at a time t. So here are the two different ways to calculate the energy stored in a capacitor. And these are the typical inductors that you can see in circuits. An inductor is simply a coil, and this coil is typically made of copper. And when we add electricity onto the coil, and it will generate a magnetic field. And a time varying flux creates a counter EMF, and which causes a voltage to appear at the terminal of the device. And the circuit's representation of an inductor is similar to the way how the inductors are made. It looks like a coil. What we care in this class is about the calculation related to inductors. And the induction law tells us the relationship between time-varying magnetic flux and the voltage generated. So the voltage generated is equal to the rate change of a magnetic flux phi-t. And for a linear inductor, this magnetic flux is equal to a constant L times the current. And if we plug this back into the voltage calculation, we find the voltage is equal to L times di dt. Similarly, we define a unit for this inductance L, which is a Henry. So 1 Henry is equal to 1 volt per amp per second. Henry is also a derived unit. So inductors store energy in its magnetic field, and they may supply stored energy back to the circuit, but they cannot create energy. So we will use the passive sign convention for all the calculations related to capacitors and inductors. So now we learned the basics about inductors. So let's see the calculation related to inductors. The most basic equation is the voltage on this inductor is equal to L times di dt. Whenever there is a current change in the circuit, an inductor will have a voltage. And this voltage is induced by the change of a current. And if a current is a constant, then the voltage will be equal to 0. That represents a steady state. When it's in steady state, the voltage drop on this inductor will be equal to 0. If we want to calculate a current, and we need to do the integration, we put L to the left hand side, it becomes 1 over L, the integration of a Vt. That is how we calculate the current. If IT0 is given, and you can take IT0 plus the integration from T0 to the time that you are interested in T. And from here, we know that the current is the integration form of the voltage. Current is continuous. So this is the continuity property of an inductor. So the continuity of an inductor tells you that the current is continuous. Let's see how we calculate the power and energy stored in an inductor. So we know the voltage and we know the current over here, right? And the power can be calculated by using the multiplication of voltage and current. And we can plug the voltage back in here, replace the voltage by L times di over dt, and this will be power. If we do the integration, it becomes the energy stored in this device. So if we do the integration of this from time t1 to time t2, and this is the energy stored during the time from t1 to t2. If you know the energy stored at the time 0 is equal to 0, and the energy will be always 1/2 L times I squared at time t, which is given here. Since both capacitors and inductors, they are passive elements, so they cannot create energy. So if we calculate the energy stored at a certain time, there should be always a non-negative number. So in your calculation, if you find the energy stored in the device is a negative number, it means there's something wrong. Alright, so now we put all these the equations related to capacitors and inductors together, and let's compare them side by side. For capacitors, the most basic equation is the current going through this capacitor, which is equal to C dV over dt. For inductors, the most important and basic equation is the voltage on this inductor is equal to L times di over dt. And from these two basic equations, we can calculate the voltage on a capacitor and the current through an inductor. On top of that, we can use what we learned from chapter 1 to calculate the power, so that we can calculate the power for capacitors and the power for inductors. By doing the integration of the power, we can find the energy stored in capacitor and the energy stored in inductors. And over here, these two equations are based on the assumption of the starting energy at time 0 is equal to 0. And by comparing the two equations, we can see that if we switch C VI to LIV, all the equations on the left-hand side will become the equations on the right-hand side. This is called a dual relationship between capacitors and inductors. In circuit analysis, majority of the time we just focus on the ideal circuits. So we did a simplification. There's always a slight difference between what we see in reality and the ideal elements. In ideal capacitor, we assume there's no leakage between the two terminals, but in reality, there is always leakage. That is modeled as a resistor or leak. But this resistor is super large. The leakage current is very small. In the ideal case, we add a constant voltage on this capacitor. There should be no current flowing through. But in reality, there is always a very small current flowing through this capacitor. And that is modeled by the leakage resistor, or leak. And similarly for inductors, in ideal case, there's no resistance in inductors in steady state. It should act as a wire, but in reality, there is always some resistance accompanied with any inductor. As long as the inductor is made by copper material, at least this copper material will have some resistance, right? For ideal case, the current through this capacitor is equal to C dV dt. In the reality, where we have the leaky capacitor, the model for a leaky capacitor, in addition to this term, we also have another term, which is voltage divided by the leakage resistance. For inductors, this is the ideal case. The voltage on the inductor is equal to L di dt. But in reality, the voltage on the inductor is equal to two parts, the voltage drop on this inductor and also the voltage drop on this leakage resistor. So which is composed of these two parts, L di dt plus the current I times R leak.